So what happens when you take sodium chloride or salt and add it into water? Well, what happens when we take dirt and add it into water? Well, let's find out. So when I take my sodium chloride and I pour some into the water, you can see initially they're still solid. If I mix it around, however, you very quickly see that it dissolves. And in not much time at all, there's no more solid sodium chloride left in the solution. So the salt has dissolved. So what happens when we take dirt and try to dissolve it into water? Well, let's see. Well, you can see that no matter how much I stir, there's always going to be solid remaining in my water. The dirt does not dissolve. So what's going on? Well, let's explore it. Hey guys, welcome to the new unit. In this unit, we're going to be talking about solution stoichiometry and the introduction to redox, or reduction and oxidation. Now that's going to be the kind of toe in the water of electrochemistry that we're going to get into this unit. The one thing I want you to be aware of in this unit is that we're essentially stepping beyond the stoichiometry that we've done so far, but the techniques are largely the same. And when we get into redox, we're going to learn some new skills that you haven't yet seen, and we're going to be able to apply them throughout the rest of the year as we keep going. So to get started, let's take a look at that saltwater solution that I prepared earlier and take a look at it at the molecular level. Now, when objects dissolve in water, it could happen in one of two ways. One way is that the water simply pulls apart the molecules of covalent compounds such that the molecules separate from each other but stay intact as a whole. For instance, when you take sugar or sucrose and dissolve it in water, the actual molecule of sucrose does not change. It stays exactly the same. But when you take an ionic substance and dissolve it in water, it actually dissociates completely into ions. Ions such as Na+ and Cl- for our sodium chloride. The way this works is that water, because it is polar, is able to form attractive forces with the ions, pulling them out of their own crystal lattice, which they're in as solid form, surrounding them, and creating a more stable end product, which is the dissolved and dissociated form of the ions. So in this unit, we're going to take a look at some of these properties of solutions. We're also going to take a look at what happens in order to create a solution, and we're going to focus on when and why solutions will form in the first place. Now, specifically, the water molecule has two sides to it. All right? We're going to talk a little bit more about this later in the year, but here's what you need to know. The oxygen side is slightly negatively charged. We call this a partial negative charge. The hydrogen side is slightly positively charged. We call this a partial positive charge. Now, because sodium ions are positively charged and chlorine ions are negatively charged, what ends up happening is the sodium ion is attracted to the oxygen atom in the water molecule. The hydrogen atom in the water molecule is attracted to the chlorine ion. And so what ends up happening is all these water molecules will act together to pull apart the sodium from the chlorine, and it's going to do this throughout the crystal lattice structure of the ionic compound. And what's going to end up happening is surrounds the ions. And that ends up creating a stable position where the ions are separate, they're in their fully ionic form, and as a result, we say that they have dissociated, which means not just dissolved, but then also come apart. Now, this doesn't happen with all things. Molecular compounds, such as sugar. When you dissolve sugar into water, yes, the molecules will separate from each other, but they will not come apart within themselves. So a sugar molecule stays a sugar molecule. So let's say it's sucrose. If you dissolve sucrose or table sugar in water, it stays sucrose. It doesn't change at the molecular level. It's simply going to be pulled apart from other sucrose molecules to to dissolve into the solution. In terms of what a solution is simply a homogeneous mixture of compounds. Now, we can make a mixture of many things. And so we're going to be talking in this unit about both mixture solutions of the form of liquids, also solutions in the form of gases, and solutions in the form of solids. And a solution can be any of those things. So the key factor here is that it's homogeneous, a homogeneous mixture. And remember, homogeneous means that it's the same throughout. If I took a subsample from any position in my solution, I would get essentially the exact same result. There are two major parts to any solution, and that would be the solute and the solvent. The solute is the thing that is dissolving. For instance, in my saltwater solution, the sodium chloride or salt was the solute. The solvent is the thing that's doing the dissolving. All right, you can also think of this as the major component of a solution. So this is the one that there's more of it. In this case, my sodium chloride saltwater solution, the water is the solvent. We oftentimes call water the universal solvent, which is true to a certain extent. It can dissolve many things, but be aware that it certainly cannot dissolve everything. We're going to get into the specifics of what it can and cannot dissolve a little bit as well in this unit. Now, in specific cases where water is the solvent, what we're going to do is we're going to actually talk about the solution as being an aqueous solution. Oftentimes you'll see this represented in chemical equations with a little AQ in the form of the phase of matter. So oftentimes you'll see solid, liquid, gas, or aqueous, AQ. Aqueous simply means it's dissolved in water. Within aqueous solutions, we can actually categorize in two different ways: electrolytic aqueous solutions and non-electrolytic aqueous solutions. Electrolytic aqueous solutions are those that can conduct electricity. Non-electrolytic, as the name suggests, cannot conduct electricity. The reason electrolytic aqueous solutions can conduct electricity is because there are ions present within the solution. So for molecular compounds like water, pure water, or sugar water, where there are only molecular compounds present, it cannot conduct electricity. They are considered non-electrolytic. Amongst electrolytes, you can actually have weak electrolytes and strong electrolytes. We're going to be talking about these differences as well. Weak electrolytes are those that only partially dissociate. So an ionic compound that will only somewhat break apart in an aqueous solution. Or they can be strong electrolytes, which are ionic compounds that will fully dissociate in an aqueous solution. So looking back at my sodium chloride example, where I took salt and I dissolved it into water, that formed an aqueous solution. Now, if I attempt to run a current through that aqueous solution, electricity will travel. It is a strong electrolyte. The reason it's a strong electrolyte is because the sodium and chlorine fully dissociate. The reason they fully dissociate is because they are fully soluble. Again, we're going to be talking about the definition of relative solubility and how you can identify relative solubilities as we continue through this unit. The other thing we're going to be talking about in this unit is once we identify whether things will dissolve or not, is then using that knowledge and understanding when we talk about the units of solutions, which is going to be molarity, which I'll introduce a little bit later to you, and also how we can actually do mathematical predictions in terms of how much product will be formed or how much reactant remains in the form of stoichiometry. Again, the stoichiometry we're going to be doing in this unit is no different than the stoichiometry you did in the prior unit. But the only difference here is that we're going to be using some new units to be able to do this math. And as a result, it can be a little more tricky. There are two different types of mixtures that are not solutions that you should be aware of, although we're not going to really go into too much depth in these in chemistry this year. Those are going to be colloids and suspensions. Now, the specifics between colloids and suspensions aren't really something that you're going to have to be fully aware of, but I really want to make sure that you're cognizant that there is a difference. Colloids are going to be these heterogeneous mixtures, which are smaller particles that, although certainly not dissolving like you would sugar, which is an extremely small particle relatively speaking, forming a solution, they stay suspended in the water column, which means that they don't settle out. Suspensions, however, will settle out. So if you look at my muddy water here, you can see that some of it remains muddy, but some of the mud and dirt has actually fallen completely to the bottom. So a suspension is one where if you were to leave it for long enough, particles would actually fall out of the water column and settle completely to the bottom. Now, one of the major ways to tell the difference between a solution and a colloid or a suspension is through a property called the Tyndall effect. Because colloids and suspensions have particles actually within the water column, what's going to happen is by shining a light into the solution or into the mixture, the light will either go straight through or it will be refracted. In the case of colloids and suspensions, the light will be refracted. So let's take a look at this using my laser pointer. Now you can see as I shine through the mixture that the light itself starts to scatter. In fact, it's not even reaching the other side of the mixture at all. Whereas in a solution, such as this, you can actually see that the light reaches the other side and is not scattered. This is how we know that we're dealing with a solution here, and in the case of my muddy water, either a colloid or a suspension. So that wraps up today's video. Let's do a quick recap. Now I've introduced you to this new unit of solution stoichiometry and redox. The key here is that we need to start by understanding solutions in general. And so the first half of this unit is really going to be focused on understanding solutions and how they work and how we can do the stoichiometry associated with solution type problems. Next, what we're going to do is we're going to finish the unit by going through and understanding how we can look at solutions in the form of electrochemistry ideas. We call this reduction and oxidation, and we're going to get there by the end of the unit. I'd like to thank R.J. Morrison for writing, filming, and editing this video. I'd like to thank you guys for watching it, and I'll see you in the next one.